This is section 5.3, part E, calculating conditional probabilities. To find the conditional probability, or the probability of B given A, we're going to use the following formula. We're going to do the probability of A and B divided by the probability of A. So in section 5.2, we classified the residents of a large apartment complex based on events A, they read the USA Today, and event B, they read the New York Times. The completed Venn diagram is reproduced here. So what is the probability that a randomly selected resident who reads the USA Today also reads the New York Times? So we're trying to find the probability that they read the New York Times given that they read USA Today. Now, we know that the probability that they read USA Today, or the probability of event A, is 40%. All the people in this circle are the ones who read USA Today, so that's 40% of the population. The population that reads USA Today and the New York Times is this part in the center, or that 5%. So given that they read the USA Today, which we put in the denominator, what percent of those people also read the New York Times? And that's 5% of them. And so if we do 5% divided by 40%, that's going to leave us with 0.125, or there is 12.5% chance that a randomly selected resident who reads the USA Today also reads the New York Times. An AP exam tip: you can write the statement like the probability of A given B is events of A and B are defined clearly, or you can use a verbal equivalent such as the probability they read New York Times given they read USA Today. So use the approach that makes most sense to you. So basically what this is telling you is if you've already defined very, very well what event A is and what event B is, you can just write the probability of A given B. If you have not defined them very well, you can actually put the words directly into the probability statement. All right, we're going to use a tree diagram backwards, and we are going to do a 4-step process for this example. So in an earlier example, we looked at whether adult internet users of various ages regularly visited video sharing sites like YouTube. The tree diagram summarizes the probability, and it is shown below. Well, the first thing we need to do is figure out what we are trying to solve. So our state for this problem could be, what percent of adult internet users who visit video sharing sites are between the ages of 18 to 29? So our plan of action, if the probability, in probability language, we want the conditional probability, the probability they're 18 to 29 given that they watch videos, we're going to use the tree diagram and the definition of the conditional probability. So we're probability of 18 to 29 given that they watch videos is the probability of 18 to 29 and they watch videos over the probability that they watch videos. So for the do, we need to look to see what is the probability they watch videos. So they watch videos here, here, and here. So if we add those categories together, we are going to get 0.4913. Again, we did that by adding all the probabilities together where they did watch videos online, and that gave us 0.4913. And then we're going to put that over the probability that they're 18 to 29 and watch videos, which is this probability right here. So if we do 0.1890 divided by 0.4913, we're going to get a probability of 0.3847. Remember, the last thing you need to do is you need to conclude. So for our conclusion, we can say about 38% of adults who visit video sharing sites are between the ages of 18 and 29. Compare this conditional probability with the original information that 27% of internet users are between 18 to 29. Knowing that a person visits a video sharing site increases the probability that he or she is young, which indicates the two events are not independent. Let's look at another example. Over 10,000 athletes competed in the 2018 Olympic Games in Beijing. The International Olympic Committee wanted to ensure that the competition was as fair as possible. So the committee administered more than 5,000 drug tests to athletes. All medal winners were tested, as well as other randomly selected competitors. Suppose that 2% of athletes had actually taken a banned drug. No drug test is perfect. Sometimes the test says that an athlete takes drugs, but the athlete actually didn't. We call this a false positive result. Other times, the drug test says that an athlete is clean, but the athlete actually took drugs. This is called a false negative result. Suppose that the testing procedure used at the Olympics had a false positive rate of 1% and a false negative rate of 0.5%. What's the probability that an athlete who tests positive actually took the drug? So we are looking for the probability that they actually took the drug given that they tested positive. So we can start this by making ourselves a tree diagram. So the athletes could have, yes, taken the drug, and we said about 2% of them take the drug, or no, they did not take the drug. If 2% do, then 98% do not. Of those who take the drug, we know that they are going to get a false negative 0.5% of the time, or 0.005 written as a decimal. So that means 0.995% of the time they will actually test positive. And we know that they will get a false positive 1% of the time. So 99% of the time they will correctly come back negative. Now, if we find these probabilities, remember you can multiply across to get the probabilities. So 0.02 times 0.995 tells us the probability that the person does take drugs and test positive is 0.0199, or about 2%. If we do this for each of the categories, now we need to find the probability that they tested positive. So tested positive is here and here. So if we add those two categories together, we're going to get 0.0297, which we will put on the bottom. Now of those, we want to see how many of them actually took the drug. So yes, they took the drug and they tested positive would be this category up here. So that's where we get the 0.0199. And if we divide that out, there's a 67% chance the athlete who tests positive actually took the drug.